All right, section 2.6 is going to focus on what we call rational functions. And you've heard the word rational more than a few times now. And up until this point, we've talked about in terms of rational numbers, which basically meant we had an integer over an integer. And anything that you could write in that form was a rational number. Well, now we're going to go beyond that, and we're going to talk about rational functions. Now, same thing, most of them are going to be set up, at least in the start, to be fractional form. So when we look at this, the difference instead of integer over an integer is now we're going to say a polynomial over a polynomial. So if we see something in that form, it defines what a rational function is. Now, one thing that becomes very important when we're dealing with rational functions is the domain. And we've done a lot of things with domain in our classes so far, and in this one it's going to be no different. Since we're dealing with a fraction, one big issue with domain is we have to make sure it's a defined fraction. So any value for x that is going to plug into our polynomial in the denominator, if it makes it undefined, obviously we can't be left with a fraction. So we're going to think in terms of what's defined and what's not defined when we're figuring out our domain. Now the other part of this is the main focus in the section that we're working on in 2.6 here is going to be on graphing, and like I said here, finding the different parts needed to draw an accurate graph. Things that you already know about in this class: x and y intercepts, so that's going to be nothing new. The part that will be a little bit different for a lot of you is we're going to also find what they call asymptotes. And there's three types of asymptotes we're going to deal with. Vertical asymptotes, which obviously vertically run up and down, horizontal, left and right, and oblique, which if you think in terms of a slant or a slope, are that type of asymptote. So that's all each of those things are. Now, as far as finding each of these things, they each kind of have their own rules, but let's first define or take a look at what an asymptote is. So let's go over to our next page here. Alright, so the first thing is, what is an asymptote? Well, a couple ways to look at this, and we'll go real basic here. If I've got my x-y-axis set up here, what an asymptote is, it's going to be a value either for x or y, if we're talking horizontal asymptotes or vertical asymptotes, that are giving us values on the graph that our function's going to approach, get very close to, but for the most part never quite reach. So we usually show those with dotted lines. So one situation could be something that looks like this. We could have a line going here. Oops, and let's get a little switch on this one. So we could have a line at x equals 3, bring it down this way, and now we've got a vertical asymptote. We can change colors here to show a horizontal asymptote, and let's say we've got a horizontal asymptote at y equals 2. Alright, so right now, doesn't really mean much to anybody other than, okay, we drew dotted lines. Now, big thing is, like I said, we're going to approach these values, get close to them, but maybe never reach them. So one way we could look at this would be, if I had a value here that was getting close to 3 as I was coming from the left, and close to 2 as I was coming down, I might end up with a curve that looks something like this. So it's almost like they're magnets that are drawing it towards the curve, and I apologize, it's not a very smooth curve there, but I'm getting closer to this asymptote, but we're not going to touch or cross them. So I can get infinitely close without touching them. So I could have the same situation happening here. I could have some point, and then I'm going to actually take that and get closer and closer and closer to x equals 3 as I get smaller and smaller and smaller. But at the same time, as I go further to the left here, I get closer and closer and closer to y equals 2, but maybe not even reaching that. So pictorially anyway, that's what our asymptotes are. And at least for this section, that's going to be our main focus, is where are they, how do they affect the graph, and that's about as far as we're going to take it. Now an oblique asymptote, only difference with the oblique asymptote is it's going to be something, and this won't make sense on this graph right now, but it's just going to be an asymptote with a slant. Simple as that. Now each of those have their own rules and so on. Let's talk about that next. Alright, so first things first, here are vertical and horizontal asymptotes. For vertical asymptotes, all we're going to do is, we've got our numerator, that's a polynomial. We have our denominator, that's a polynomial. For our vertical asymptotes, what we're going to do is set our denominator equal to 0. So basically, we're finding our domain. Whatever values of x give us 0 for the domain, those are vertical asymptotes. Pretty simply put. Alright, horizontal asymptotes, not quite as clear cut, because there's 3 separate rules that we're going to deal with. If I look at a function, and let's say up on top here I have a sub n, x sub n, plus blah 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 the rest of the way out, and on the bottom I have b sub n, or m, x sub m, plus all the way out. So polynomial on top, polynomial on the bottom. There's going to be a couple different things we're going to look at on here. Alright, so our first situation would be, we're going to take a look at n and m, and we're going to make that comparison. So when we look at that, there's actually 3 things that can happen. The value of n up on top can be less than the value or the exponent of m on the bottom. They can be equal to each other, or the exponent on top can be bigger than the exponent on the bottom. Each of those things is going to give me a different situation that happens for my horizontal asymptotes. So here's what the situations are. If the top asymptote, or the top exponent, sorry, is smaller than the bottom. So if this was x to the 2nd power and this was x to the 3rd power. So top is smaller than bottom. If that's the case, my horizontal asymptote is at y equals 0. In other words, the x-axis itself becomes a horizontal asymptote. My situation here, if they're equal to each other, so let's say it's 2nd power and 2nd power, then what's going to happen is I'm going to take a look at my 2 lead coefficients. And what's going to happen is y equals that first coefficient over the 2nd coefficient. That line is going to become my horizontal asymptote. So if this was 2nd power and 2nd power, and the lead coefficient on top was a 3 and the bottom was a 4, I would get y equals 3/4. So I would go up 3/4, draw my dotted line, there's my horizontal asymptote. Now my last situation, n is greater than m, so maybe 3rd power on top, 2nd power on the bottom, I'm going to have none. There will be no horizontal asymptote. Now there is one situation that's going to be a little bit different, and that's if n is greater than m by exactly 1, then that's going to give me my oblique asymptote. And what I would do with my oblique asymptote, if this is true, I would take everything on top up here, n, that polynomial, divided by the bottom polynomial. And I would do long division. And we did some of that in an earlier video. So if that was the case, I would do the long division. Whatever I get up on top for my quotient, y equals is going to be the equation of my oblique asymptote. Whatever my remainder is down here is going to have absolutely no effect on this. So all I'm looking at is whatever I get on top of my long division is going to be the formula or the equation of my oblique asymptote. And again, that only happens if this is like fourth power and this is third power. So the top is bigger than the bottom exponent. There are no horizontal asymptotes in that case, but if this is exactly one bigger than bottom one, then we've got the situation of an oblique asymptote.